right? Now they really are just messing with me, right? This week we're going to talk about power and root functions. Really, this means powers that are not like whole numbers, like integers, because we already know how to deal with those. Natural, like positive integers, that's just a polynomial term. Negative integers, that just means the same thing as something like 1 over x squared. So really, the new stuff that we're adding on, what we're talking about this week, is how we deal with powers that look like fractions, decimals, that kind of thing. And we're mostly going to focus on rational exponents. Again, anything rational means, think fraction. So exponents that are fractions. For example, something like x to the 1/2. And just so you know, the way that, because putting a fraction in an exponent makes all of the like typesetting stuff go kind of bonkers with how it like places things. I'm going to write stuff like that. Generally, that means the same thing as x raised to the 1/2 or x to the 1/2. Sometimes you might see it kind of more in line like that. These all mean the same thing. X to the 0.5. I'm going to handwrite stuff like this, but in type stuff, it might look more like that. But again, they all mean the same thing. The exponent is 1/2. What we need to figure out then is how this works. Any ideas? Let's think about the fraction part for a second. We've been talking about fractions a lot lately with all the rational stuff. So let's just think about kind of breaking that down for a second. The denominator of a fraction tells you something about what kind of thing it is, right? And that's why we have to do all the common denominator stuff when we work with them. If I want to add, a 1/2 and a 1/3, what we do first is get them into common terms, right? Get them to the same kind of denominator. So we're talking about the same kind of thing. You want to think about it as, how big of a slice of pie we're talking about or whatever, the sort of elementary school version of fractions, that works here too. So the denominator is something about what kind of thing it is. The numerator well, again, thinking about this means take the pie or pizza or whatever and cut it into 2 slices and keep one of them, right? This means cut it into 3 and keep one of them. The numerator is how many of them? Okay, so let's figure out what on earth x to the 1/2 means. If we're not sure, let's just try doing something to it. Whatever it is, let's square it. What is this? IDK, let's try something. By the way, on something like a test question, don't just write IDK and move on with your life. You can write that and say, but I'm going to try something. But when all I see is like, I don't know, and I don't care to try either, it not only means you're not going to get any credit, but it also means I'm going to be a little bit angry about what's happening. So like, just try something, do something. All right, x to the 1/2 squared. How do you square something? Multiply it by itself. What do you do with the powers then? You add them, right? You got the same thing. You're multiplying it together. You add the powers together. What's 1/2 plus 1/2? 1. Hey, oh, hey. That's just x to the first power. Okay, so whatever x to the 1/2 is, it's the thing that when you square it, you get eventually x back, right? You can also do this directly. How do you deal with a power raised to a power? You take a thing with the power and you raise it to another power, you multiply the exponents. And that would also give you x to the 1. Okay, so however we think about breaking down the exponent rules for doing the algebra and combining, whatever this is, x to the 1/2, it's the thing that when you square it, gives you back x. Do we have a name for that? The thing that when you square it, gives you back the thing underneath or inside? We've already got all the leaves there. I know how fall works. They're not back already. When you, oh crap. When you square a thing and get something back, that means that the thing that you started with here was the square root of the thing you ended up with. So x to the 1/2 just means the same thing as the square root of x. The way a square root works, you take a thing, the thing inside, the x here, the radicand is the name for that. You take it and you break it into, for square root 2, equal pieces that when you multiply, give you back that thing, right? So the square root of, I don't know, 9 is 3 because 3 times 3 is 9, right? So this what kind and how many thing, the 1 is like a normal power. It's how many of them, right? This is 1 square roots of x, or it's the square root of x to the first. The denominator, the what kind of thing part, that's how much you're breaking it up, right? A normal denominator in a normal fraction means you're dividing it, right? It's division, it's breaking things up. In an exponent, the thing that division sort of becomes in the kind of exponent like environment is that it becomes a root or a radical. So this 2 is the index or the type. That's not that whole word. Now the square root symbol already means the square root, so we don't normally write the index 2, just like we don't normally write the exponent of 1, but that's what that 1/2 power means. So how would I make sense of x to the 3/5? It's a 5th root, which means instead of breaking it into 2 pieces, you break it into 5, but they're all the same. And when you multiply them up, you get the thing back of what? X to the 3rd. Fifth root, x to the 3rd. Okay, now because these things are both multiplication, right? The root and the normal power, the cube, right? That just means 3 copies of it and multiply them together. Because they're both multiplication, it doesn't matter which order we do them in. So that's the same thing as the 5th root of x, all to the 3rd. Depending on what we're doing, and we'll get more into this today and probably more tomorrow, but depending on what we're doing, sometimes it might be more useful or more straightforward to think about something this way. So other times it might be a little more straightforward to think about it this way, but being able to kind of be a little bit flexible about going back and forth between those two things is often helpful. There we go. Finish highlighting everything. Okay. Now, if I'm doing this for something like a number, which you'll see some in the homework, like 8 to the 4/3 or something. You can just, I mean, you've got a calculator, right? You're carrying around the sum total of human knowledge in your pocket all the time. So you can just enter that directly, 8, little caret thing for the exponent, and then 4/3. Probably you want to give the 4/3 a set of parentheses if you're typing it into a calculator. What this means, though, is the cube root of 8 to the 4th, or I can think of it as the cube root of 8 to the 4th. Now, for whatever reason, I'm trying to, do this like by hand, and I'm mostly just doing this as like an illustration of why we care about having two different ways to write the thing. 8 to the 4th, I don't know what that is. I could, get a piece of paper and, multiply a bunch of 8s out and figure out what that is, but it's going to be big-ish, right? 8 to the 4th. And then I need the cube root. I don't have any idea how to like do that cube root by hand. What's the cube root of 8 though? 2. And what's 2 to the 4th? 2, 4, 8, 16. That I can do by hand. This one just makes me sad, right? So like they're the same, but again, there are reasons for, having sort of two different interpretations or takes on it. On the other hand, if we're doing something like solving an equation, there might be times where, where imagine this is like an X or some unknown thing that we're solving for. Maybe looking at it this way would be a little more straightforward than dealing with it the other way. So the main point right now is just being able to kind of go back and forth between those. So one more maybe. What's the how would I write that as a power of X? So it's 2 over 7, right? It's a 7th root, which means the denominator's got to be 7. There's a square, so the numerator's got to be 2. And also, this is the reciprocal, right? It's in the denominator, it's 1 over that. So how do we make that part happen? Make that whole exponent negative, right? So this whole thing is the power there. X to the negative 2/7 would be the reciprocal of X to the 2/7, which would be 7th root of X squared. Okay, so just kind of going back and forth between those things. Again, once you do a couple and it kind of clicks, you should be able to pretty much just kind of look at it and write it down. There's not really anything to work out there. Okay, cool. I haven't handed you notes yet, have I? So today we're mostly going to focus on functions involving either a square root or a cube root. And just like we did with the other stuff, we're going to see what we can generalize. Yeah, my bad accounting. Okay, so let's just remind ourselves real quick about the two of these that we do already know, which are the square root and the cube root. it's been a while, but these were two of the very first, group of functions that we looked at and did transformations with and all that stuff back in, September or whatever. What does the square root function look like? Something like that, right? So there's a point at the origin, and then it just kind of curves upward like that. It's one side of a parabola that's flipped over on its side, right? So getting from the square to the square root, obviously those things are related as like operations, right? They're kind of opposites. That means as functions, they're inverses. The problem is x squared is not 1-to-1, right? Doesn't pass a horizontal line test. So if I just take the whole thing and flip it over on its side, I get a thing that's not a function. That's why when we solve stuff like x squared equals 4, right? What do you do to solve that? Take a square root, but when you take the square root, you don't just get the obvious one, you also get a plus or minus that comes along with it, right? And that plus or minus is a thing that like we just kind of have to remember, but it's because of the way this whole thing works, this inverse relationship between these. This is not 1-to-1. So in order to have a square root that is a function, right? In order to have a calculator button for the square root that like knows how to just spit an answer out, we have to restrict this, which means we have to restrict this, which means it's just the upper half, just the positive one, right? The square root function would give me just +2 here. The -2 comes from the sort of missing, invisible, like lower half of that thing. And that's part of the reason that a lot of the stuff we've dealt with for the last month, right? Like think quadratic formula and solving quadratics and all that stuff. That's part of the reason all that stuff comes along with is because, well, to make it a function, I gotta, kind of throw half of it away, but it's sort of gone, but not, so it leads to a lot of that weird stuff that we've seen come up, like anywhere there's a plus or minus in solving things. What's the domain of that function? It would be 0 to infinity, and the range would also be 0 to infinity. That again is going to how this translates to that, how the whole thing works. When you take the square root of a number, if you want to get back a real number, that thing underneath the radicand, the inside of this x, had better be non-negative, right? Because if you take the square root of a negative number, we get into imaginary stuff. When we graph and we talk about domain or range for a function, we're only interested in real numbers. That's why this does what it does. Okay, what about the cube root? If a square root's a sideways parabola that we had to cut up and throw half of it away, then a cube root's going to be a cubic flipped over on its side, right? Because those things are opposite if we think of them as operations, right? You want to undo a cube, you take the cube root. The difference is this thing doesn't have the same problems that x squared does, right? The cubic is 1-to-1. This is a function. It's also 1-to-1. So if I turned it over on its side, I don't have the same stuff to worry about. I get a thing that looks like that. That is a function. It's also 1-to-1. It's odd if you look at the symmetry, but it doesn't have the same issues, the same restrictions that this does. The domain there is everything. And so is the range. Those ends are pointing, left and down and up and to the right there. So everything gets covered. Just like with polynomials, if you go higher in the index, so this is index 2, This is the index, is 3 there. If you go higher, 4, 5, 6, a million, whatever, the same thing's gonna happen, right? The only difference is that, the graph's gonna get a little more kind of squished in, right? If I looked at like a fourth root compared to a square root, it's just gonna squish in a little bit more. But it does the same thing. It works the same way. Same idea here. If I look at the seventh root or something, it's gonna look a lot like this. So it's all tied to that index being even or odd. Just like with polynomial stuff, the end behavior was heavily tied to whether the degree was even or odd, right? The index here does kind of the same thing. Okay, so what if we need to find the domain of some function that has a square root in it? It's 3x minus 6, right? Yeah. What could we do? It's a square root, so it's going to look generally like this, right? If I want to think through transformation stuff, this times 3 does some stretching. It changes the shape. It doesn't move it, but it does change the shape. What about the minus 6? Moves it where? How? To the right? By how much? 6? Okay. Well, here's the graph. In case you want to compare. There's the square root with nothing going on. So it's a little bit, taller, kind of squish. So the shape has changed a little bit, the stretching part. But more importantly, what happened here? It didn't go 6, right? The shift was by 2, not by 6. Here, the 3x minus 6, don't worry about the details so much necessarily, but when shifting, stretching, reflecting, when those are all happening in the same direction, like left and right here, when they're all happening in the same direction, they all kind of affect each other, right? They all kind of intermingle in ways that are not always super easy to kind of pick out all the details and figure out exactly what happened. Here, to deal with that 3x minus 6, you basically have to treat it like 3 times the quantity x minus 2 to really see what's going on. You have to like factor that 3 out, kind of hold it out of this stuff. The 3 does do a stretching thing, but the shift is only by 2 rather than by 6. And that's not the easiest thing to keep track of or to, pick out the details. So like we can do that. That does work. Transformations. Shift to the right. 2, again, for kind of dense and hard to spot reasons, maybe. And stretch horizontally by a factor of 3. So the domain is 2 to infinity because we shifted it to the right, but didn't change anything else about like where it is or which direction it's facing. But again, picking out those transformations can get kind of complicated. Like look at the 4 practice problems there in the middle of the page of the notes. If you look at some of those, doing this same kind of thing and like really detailed analysis of what each thing is and where it comes from and what it does is going to get kind of tricky. So another way that we can look at this that's a little more concrete or a little more mechanical maybe. What's really happening here with the square root function? Forget about the fact that that's an x for a second. I took the square root of something. What this says is that the something has to be 0 or bigger, right? The domain being the closed interval from 0 to infinity means that I can't allow negative numbers to go in there. I can't, x can't be negative. So what's really happening here is that the radicand, the inside, has to be 0 or bigger, right? It can't be negative, because if it was negative, we're talking about the square root of a negative number. That's imaginary. That's outside the domain of a function that lives in the real plane. So how could I use that to figure out how to answer a question like this? Whatever this is, if the function is going to be defined, that the stuff inside the stuff I've highlighted has got to be 0 or bigger, right? It's got to be positive or at least 0. Well, really, that's just an inequality, right? What we're describing is an inequality. The inside, which is 3x minus 6 here, has to be, I'm going to start saying non-negative because I'm tired of saying 0 or bigger, 0 or positive, right? 0 or bigger. That's what non-negative means. It can't be negative. So really what we're saying is 3x minus 6 has to be greater than or equal to 0. Oh, hey, that's the thing that I can use, algebra skills. I don't just have to pick things out and think about where each thing came from and, have this really like insightful analysis of what's going on. Now I've turned it into, a math problem, or a thing that feels more like a math problem. Figure out where it is 0, which is a 2. Oh, hey, 2, that's good. Like I already know the answer here because we looked at the graph. I know that 2 was important. 2 just showed up, right? What we need to know is what happens on either side of 2. If I let x be 0, that function would be the square root of 0 minus 6. And the square root of a negative number is I. It's imaginary. It's not real. It's not in the domain. On the other side, if I let x be 4, I get the square root of 6. Now, I don't care about the fact that it's, 6. I care about the fact that this is imaginary and this is real. Domain of a function, range of a function, whatever, we're always talking real numbers. That's all that we know how to graph at this point. That's what we see when we graph things. So the domain then is this part. It's 2 to infinity. And now we have a way to approach the thing that doesn't rely just on me being able to correctly figure out what each little bit of stuff does to transform the graph and how those all interact and fit together. So if I look at G, the one like lower left there, -3 minus x over 2. That's got a stretching thing, it's got a reflecting thing, and it's got a shift. Again, they all interact. None of them you can just like read the number off or whatever. So there's a lot going on there, but if I approach it kind of using algebra skills, and this is one of the reasons that talking about inequalities matters in the first place. I mean, yeah, we can use them directly in applications, but we can also use them to do stuff like this as a tool to answer a different question. Okay, so let's take a couple of minutes. You guys give some of the, oh, wait, sorry. We talked about square roots. We haven't talked about cube roots. If the index is odd, how does the domain work? It's all real numbers. It's defined everywhere. If I take that and move it to the left a little bit, is that going to change the domain? Move it to the right. If I reflect it this way, stretch it, shrink it, any of that going to change the domain? No, it's defined everywhere, right? If it's defined everywhere, then it's defined everywhere. It doesn't matter if you shift it around or reflect it or do those kinds of things. So if we're looking at the cube root of something, probably we don't really have as much to worry about or as much to work out, because the cube root itself isn't going to like add anything into the domain question, right? Into figuring out what the domain looks like. So there are 4 practice problems in the middle of the notes right here. Let's take 5 minutes or something. You guys try some of those. Find the domain of those functions. Okay, so let's talk about a couple of these. We want to find the domain of this function. F of x is the square root of 5x plus 3. Thinking about domain, looking ahead to test on Friday, final exam, whatever. Finding the domain, if I'm asking you to find the domain of a function that I give you like this, probably the thing that you want to be thinking about is what could go wrong, what kind of like bad stuff do I need to look out for. Think about all the rational stuff we've been doing the last couple of weeks. There we need to avoid dividing by 0, right? Because dividing by 0 is undefined, you can't do it. This is a square root. What do I need to be thinking about then to figure out what the domain of this function is? What could go wrong? What kind of bad stuff could happen here that I need to, avoid? The whole thing being imaginary, which would mean that the stuff inside or underneath is negative. The inside can't be negative, otherwise the whole thing would be imaginary. Okay, well, just like we did with rational stuff, the way we figured out, where it is defined, what its domain is by figuring out first where it's not, right? Like there, we took the denominator and set it equal to 0 and then said, okay, well, the domain's everything else, right? We do the same thing here. Take the inside stuff aside. And what I need to know is where that's positive and where that's negative, which means I need to figure out where it's 0. Which would be -3. So -3/5. Once I divide that 5 over. Now again, if you want to think about it as transformations, there is a shift to the left, but the 5 and the 3 kind of affect each other. So it's not by 3, it's by -3/5, which is, again, kind of weird. But then what happens is that if I take this thing and shift it over and stretch it out somehow, to the left of -3/5, this would be undefined. Because if I plug -2 in, I get -10 plus 3, so -7, which is imaginary. If I plug 0 in, though, I get 3, which is real. So the domain is everything from -3/5 to positive infinity. It's equal to 0 right here, and then anything to the right of that is going to be fine. If you want to think about it graphically, and you can even graph it in your calculator, it looks something like this, right? So the domain is going in the direction of positive infinity. It just cuts off at whatever this value is. That's the part that we need to go find, right? Yeah.
Can't you just set it up as the inequality we did and then just say that?
If you want to just solve it as an inequality, that's fine too. Yep.
Well, not only that, can't you just say that, x is bigger than or less than -3/5, which means it has to be
Yeah.
-3/5, which is in which bracket?
Yes, right. So there are several ways that we can approach kind of the, proving it part, right? Getting to the answer. Just graphing it and, your calculator's not even gonna give you this. It's gonna give you -0.6 if you know how to find it. We probably need to do a little bit more than that, right? Like I would want to see at least that like solve to find -3/5 or something. Then if you want to use the graph to justify why it's from there to positive infinity rather than the other way, that's okay. If you want to just straight up solve this as an inequality, that's fine. It's linear, so nothing too weird happens. If you divide by a negative, you got to remember to flip, so be careful about that. If you want to just kind of brute force it, which is pretty much what I did, that works too. Like any of these things is fine. As long as we're sort of doing enough to like really prove our point, right? So yes, that would be fine. If there's more going on, then you want to be careful with the inequality. Okay. Now this looks different, right? This doesn't look like it's even the same kind of thing, except what does that 3/2 power mean? It's a square root and a cube. And again, just for sake of a reminder, those are the same, right? So we can treat it either way. Now, does it matter which way I sort of read or think about this thing here? If I'm thinking about the domain here, look at the stuff inside, -3 minus x/2. That's just normal arithmetic stuff, right? That doesn't affect domain. It's gonna, affect like where it lives, where it ends up, but there's nothing there that would be like undefined, right? What else is going on? There's a square root. Does that affect domain stuff? Does that give me stuff I need to be careful about? Yeah, right. This whole conversation we've been having. Does the cube do anything to affect how I answer the domain question? What do cubic functions look like? What kinds of things can you do with a cubic function? Can they handle negative numbers? Sure. 0? Yeah. Positive stuff? Sure. Right? So this, whether I treat it as being outside or inside, doesn't really add any extra information into how I figure out the domain, right? Like that's not really going to affect anything. So what I need to be concerned with then is just figuring out, again, because it's a square root, where this is positive, or where this is positive, or I'm just going to forget all about this because it doesn't really, change how I'm going to handle things anyway, right? So we just do the same kind of thing as before. Solve that inequality either by solving the equation and testing, by solving the inequality directly, by solving the equation, then looking at a graph to see what's happening or thinking about the transformations. I'll warn you though, again, about just trying to do it purely by it moves like this and it does this and that, because there's a lot going on here, right? This is a stretching thing by a half, which means that this shift is really 6, not 3. You have to kind of factor it out, and that gets weird. There's also a reflection. So I would be careful about just doing it that way. But if you solve the inequality, again, that kind of automates stuff for us. I want to just solve the equation so I don't have to worry about flipping signs. So -6 is the like threshold, that's the cutoff. And then again, I just need to know what happens on either side. If I plug 0 in, I get -3 under the square root. If I plug -10 in, I get 5, 2. So what's the domain then? -infinity to -6. That reflection turns the thing around, so it goes the other way. Okay. Real quick, and you finish up the other two that we didn't do. Real quick, we'll spend tomorrow talking more about solving equations, but how would you solve something like this?
You would just square x and square.
If I square that, then the square root goes away. If I square that, though, I got to square the whole thing. So x would be 16 then, right? 4 squared. Okay. What if this had been the square root of x minus 1? Add the 1 to both sides. Move it over. Do easy stuff first. Then what? Why is it so important to do that? That's right. That's correct. Why can't we do it in the other order and square first? If you square first, when we do that, we're not squaring just wherever we feel like it. We're not squaring just individual pieces. You're doing the same thing that you always do to solve an equation, which is do something to one side and do the same thing to the other side, right? It's got to stay in balance. So really, in some sense, like you're doing it to the equation as a whole all at one time. If you square that whole side, that means take 2 copies of those things and multiply them together. And that is that. And that is objectively worse than what we started with, right? We started with just the square root of x. I got to get rid of that somehow. Okay, fine. Now I've got a thing that not only still has that, but it's also got this other piece that, like, I can't, they're the same kind of thing, but they're not like terms, so I can't combine them. This is worse than what we started with, but we can avoid it easily enough by just moving the 1 over first, right? So the main thing that we want to keep in mind for solving stuff, we'll get more into details tomorrow, but is isolate the messy part first, the square root, and then go on and do stuff, right? All right, y'all have a good day. I'll see you tomorrow. Let me know if I can help with